Yeah, okay. I have started the recording. Yeah. Okay, let's start for today's classes. Okay, today's class. In the past 3 weeks, we talk about some features about classical physics, like Lagrangian, Hamiltonian. Then we move to atomic spectra, okay, where we introduce some features of quantum mechanics, like Planck constants, right? And then we move to the Schrodinger equations, which is the building blocks. I would rather say building blocks of quantum mechanics, and we also see some examples of quantum mechanics, like potential well, like particle in a potential well, and so on. Now we will move to the next part, which is of quantum mechanics, which is called perturbation theory. Okay, perturbation theory. So whatever uh, the terms which I'm writing it here, I have taken it from of this textbook called Zedley, uh, Introduction to Quantum Mechanics by Zedley. And if you look at the chapters number 10, you will encounter about the time independent time sorry time independent um perturbation theory. So this is from chapter number chapter number 9, sorry. Chapter number 9 is the time independent perturbation theory. Okay, so if you want, if you need any reference or details, you can look at this books. Okay, all the details are there. Okay, so so if you remember, if you have any Hamiltonian and operate on the state psi n, you will get energy n, right? This is what Schrodinger equation says, that if you like from the Schrodinger equation, if you operate Hamilton on the state function, you will get the energy values. Okay. Now, but what happens is that in most of the real situation, you will be encounter situation like your Hamiltonian is H naught plus HP. Okay, so H naught is your original Hamilton, where HP is your perturbation Hamilton. Okay, this HP cap is very less compared to your H naught. Okay, or we can write HP as lambda term W, where lambda is very less than 1. Okay, so now equation 1 becomes instead of H, you will put HP, H naught plus of HP plus H of P is lambda W. Okay, operate under state psi. Let's say you operate under state psi, you will get something like En psi n. Okay, and this En is different from whatever you get. Okay, in the equation 1. Okay, so what does it mean? It means that suppose if you have an ordinal systems and you slightly perturb it means you put some disturbance, a little of this disturbance, and then you have to find out what is the energy of the systems. Okay, that is what it means. So here HP is perturbation. That means you introduce some could be external disturbance, slightly descending, and that is why your HP is to be very less than H naught. Okay, your original systems. Okay, that is what it means. Now, so what happens is that when you calculate the energy En, okay, it will be En0. En0 is your original energy, plus you have to introduce correction lambda En. This is the first order correction, second order correction, and so on. Okay, so because of your perturbation potential or perturbation Hamiltonian, you have to introduce this correction terms in your energy. If there is no perturbation, then you will get En is equal to En0. If there is a perturbation, then you have to introduce your correction En1, that is the first order correction, En superscript 2, which is the second order perturbation. Okay. Now, so how do we, okay, other than the energy also, similarly, you can write the wave function as, this is your original wave function, plus lambda psi n1 psi square, and so on. Okay, in the wave function also you have to introduce a correction terms. Okay, now So some formulas, okay, which you will need, okay, while solving problems, okay. These again can be easily obtained from your textbook, okay. So I will not derive it, it's not required for this particular classes. So the first order term en1 is given by phi n mu phi n, okay. Next, so then the energy En will become En0, which is your original energy, plus your first order correction term, which is phi n, and let's say perturbation potential and phi, okay. And similarly, psi n, that is the first order correction, will be phi m, look at phi n, En0 minus of Em0 phi m. Okay, so just take this formula. When we solve these problems and we will solve these problems, we will be like, we will understand more. Okay, so other than the first order correction term, we also have second order correction term, which is En2, right? Second order correction term is given by n phi m w phi n whole square by En0 minus En. Okay, so if a given problems is given, okay, and if there is a perturbation problem, you have to solve the first order correction term, and if necessary the second order correction term, and so on. Okay, so last class there was one problems, the last problems of the week 3, which the problem is related to this particular classes. That's why I didn't take the last problem last class, so we will do it this time. So this time it will be the question number 5 of your last assignment, okay. That is a week 3 assignment. This is question 5, week 3 assignment. Okay, so what it says is that consider a two-dimensional infinite square well as v of x equal to 0, x is less or equal to a, and y is also greater than 0 to a, and infinity or x. So this problem we have seen last class. This is an infinite potential well, okay, and if there is no perturbation, then you can easily solve it. But now, if a perturbation, now you introduce another perturbation of h prime equal to, let's say v naught, x less than 0 to less than a, and y greater than 0 and less than a, okay, always 0 always. Okay, so if you remember, if there is no perturbation, then the solution of such problems where it is an infinite potential box, right, is easily given by psi is equal to root 2 by a sine of n pi by a x. This is the original wave function solution, right? If you solve this x is equal to 0 to a, and in a one dimensional, I'm talking this is a one dimensional solution. But here there are two things. One, it is a two dimensional, which is x is given to you, x is greater than 0 and less than a, y is also greater than 0 and less than a. Otherwise the potential is infinite. Okay, so what does it mean? It means that if you look at it, last class we talked about 0 to a. This is in one dimension. Let's say this is the x-axis, but now there is also a two dimension. Okay, so it will be different. So the energy term will be what? Energy term, it will be pi square h cross square by 2ma square nx square plus ny square. Okay, so you have to add the nx square plus m square. If you remember, in the one dimension, what do we have? We have En is equal to pi square h cross square by 2m a square, or n square pi square h cross square by 2m a square. But now since it is two dimension, your n square will be nx square plus ny square. And similarly, the wave function psi, now it will be nx comma ny, because it is a two dimension. It will become to what? Root 2a and square root of root 2a, root 2 by a into square root of root 2a. Anyway, it will be coming. It will be multiplication 2a and sine of, now it will be nx pi by ax, pi x by, sorry, nx pi by a into x and sine ny pi by a into y. So what is happening here? In the, you just multiply this sine x into sine of nx pi by ax into sine of ny pi by a y. How do we get that? We get it from your original equation. Ordinal equation, that's the equation. Ordinal equation 1. Okay, this is the ordinal equation with multiplication 1. You just multiply this terms of nx and ny. Okay, so that is easy. This is in two dimension. This is without perturbation. You get the energy directly by solving the Schrodinger equation. Okay, now the question is the question is we have to solve the first order correction. Okay, we have to solve the order correction because there is a perturbation. Right, now first of all we need to find out what is the ground state energy. So so the ground state energy will be without correction is given by, you have nx equal to 1 and ny is equal to 1, because here nx can go from 1 2 3 and ny is also 1 2 3. So the ground state means the lowest energy state. Okay, the only possible is that nx is equal to 1 and ny is equal to 1. This is the lowest energy state. So if you put that, energy E11 will be equal to what? Nx is equal to 1, ny is also equal to 1. You will get pi square h cross square by 2ma square, correct? And then we get 1 square plus 1 square. It will be equal to simply pi square h cross square by ma square. Okay, so fine. That means this is the energy without the perturbation. Second, the first excited state. Ideally, for one dimension, you will have n equal to 2. But here, since it's a two dimension, you have again two possible things. For the first excited state, you will have either nx equal to 1 and ny equal to 2, or possibility is nx is equal to 2 and y equal to 1. And if you calculate, they have the same energy. En will be equal to En, or I will rather say E12 is equal to E21, which is equal to 5 pi square h cross square by 2ma square. Even though these two states are different, right? In the first case, you have nx is equal to 1 and ny is equal to 2. Whereas in the second case, nx is equal to 2 but ny is equal to 1. These are the same. Why I'm considering this? Because they have the same energy. If you put back in this equation, En, which is equal to pi square h cross square by 2ma square, let me just name it as equation 2, you will get exactly the same energy. Okay, so that is why this is the energy of the first excited state. Now, the question is we have to solve the energy corrections. Okay, we have to solve the energy correction. So as I've just told you, that in order to solve the energy correction, we have to use this formula, right? Energy correction, right? En1 is this formula, right? En2 is again this formula. Then we will add in the energy terms. So what you will have to do is that there is a concept called secular equation, okay, which is given by a determinant of W minus of lambda I, or instead of lambda I will write energy 1, that is the first order correction, into the identity matrix equal to 0. Okay, where wij is equal to psi I h prime psi j. Okay, so we have to first solve this equation, and then once we get w11 w12, then we can put back in this equation to solve the value of en. So the idea is that we have to solve this term here, because this is the first order correction term, right? Since it is a two dimension, what you will have is that you will have w11, or again you will have also w12, right? You will also have w21 and you have w22. These are the possible terms, right? Now we will first solve w11. W11 means you have to solve only the perturbation. Now the perturbation, the integration will go from 0 to a by 2, not 0 to a, because 0 is the whole potential well, but here the perturbation is only 0 to a by 2 as given in the problems. 0 to a by 2, 0 to a by 2. So that is why when you solve the problems, you will take 0 to a by 2, 0 to a by 2, and what will happen? You get psi, and then the potential is given to be, perturbation potential will be V naught, right? And then again psi 1. Let me take as psi 1, and then we get dx dy. Okay, so what is now you this is constant, you can take it outside, so you'll get 0 to a by 2, right? So then what happens, you just multiply psi 1 with psi 2. So but before that, okay, so sorry, before that let me just write an energy term here. Based on this, you also have to, I forgot to write the wave function, sorry. Yeah, so first one is the psi 1 term is given to be psi 1 or psi 1 of x comma y is equal to, let's say, psi 1 to x comma y will be equal to what? Same thing, 2 by a, because it will be multiplied just like in the first case, psi of nx, then it will be sine of nx is given here, nx is 1, so pi by ax, and sine of 2 pi by a 1. Correct? Because nx is equal to 1 and ny is equal to 2. So you can write again the wave function for this first excited state. Just like we have write the Schrödinger equation for the ground state in this way, right? The ground state of psi of nx and y. Here also we do the same thing. Now psi 2, which is again x comma y, which is you can write as psi 2 1 x comma y, because there are two states, okay, with the same energy. So psi 2y will be equal to 2 by a is the same thing, sine. But in this case, n is equal to 2. That means these sections here, n is equal to 2. So that means 2 pi by ax and sine pi by a y. Okay. Now that means you know now the wave function. Why I write this wave function? Because you will need to solve this part here. Because you need the wave function psi. Correct? For the first excited state, you need this wave function. So now psi 1, you know, you can put this one psi 1. Okay, and psi 1 again, psi 1, it will be psi 1 square. So it will be, you will get something like psi 1 into psi 1, you can multiply it, you can get 2 by a sine square pi by ax dx, and your y will be 0 to a by 2, 2 by a sine square 2 pi by a y dy. Okay, because psi 1 into psi 1. So now if you solve these problems, you will get something v naught divided by 4. Okay, again you can solve this integration, which is a simple integration, sine square, or you can use the trigonometric sine square x is equal to 1 minus of cos x by 2, cos of 2x, cos of 2x by, then you can do the integration, you will get v naught by 4. Okay, similarly, since v11 is the same thing as v22, which is equal to v naught divided by 4. Now we just need to solve w12 which is also equal to W to 1. So in this case, what will happen? It will be 0 to a by 2, the same thing for x, 0 to a by 2 for y, right? And psi 1 v naught, I will rather say psi 2 dx dy. So again, v naught will be taken out since the constant. Then you will get something like 2 by a, integration from 0 to a by 2. Again, you put integration of psi 1, will get something like sine of pi by ax, and sine of 2 pi by ax dx whole square. Okay, and you will get this integration to be v naught 4 by 3 pi whole square, which is equal to 16 v naught divided by 9 pi square, w12, which is equal to w21. So you can put the integration. Okay, psi 1 and psi 2 I have already given. This is just a standard integration. Okay, so you will get 16 v naught divided by 9 pi square. Okay, so now what we need to do is that now we get what is v1, what is w11, w12. So circular equation will be v minus of e and 1I, correct? That's the determinant equal to 0. So now you got this w. So your w will be equal to what? W11 is v naught by 4. W12 is 16 v naught divided by 9 pi square. And here also 16 v naught divided by 9 pi square. And finally we get v naught divided by 4. Okay, and minus of, let's say, en1 1 0 0 1. Okay, okay, so which will be equal to 0. This is the determinant. Okay, now what you can just write it out, it's very simple. Now you can write v naught divided by 4 minus, so en1 into 1 will get something like en1. This term will become 16 v naught divided by 9 pi square is the same thing. You just solve this matrix. Okay, and 16 v naught divided by 9 pi square, which is the same thing, and v naught divided by 4 minus this term en1. So this is a determinant question, right? So the determinant is that this and this will get multiplied, so will be v naught divided by 4 minus of en1 whole square minus, again this will multiplication will be 16 v naught divided by 9 pi square whole square equal to 0. So if you do this, you will get v naught divided by 4 minus of en1, that is the first order constant term, square equal to 16 v naught divided by 9 pi square whole square, right? So en1 will be equal to what? En1 will be equal to v naught divided by 4 plus minus 16 v naught divided by 9 pi square. Okay, so the ordinal energy which you will get is E0 plus of En1, where En1 is given by this one. So you will get En prime is equal to E0 plus this term V naught divided by 4 plus minus 16 V naught divided by 9 pi square. Okay, that is the correction term. So so the idea is that if you have a perturbation, you will have the ordinal energy plus, okay, plus the correction term energy. So that correction term energy you have to solve it based on the perturbation potential. Okay, so similar problems. Now we will move to your this week 4 question number 1, week 4 problem. Okay, week 4 problem which is related to your hydrogen atom. Okay, in this case also what we will do is that all of these problems are related to your perturbation problem. Okay, so question number 1, week 4, it says that consider a hydrogen atom. Consider a hydrogen atom which is subjected to small perturbation. Again, here also you are encountering the word perturbation. H prime. This is given the perturbation as lambda r square. Okay. So use the first order correction to calculate the energy of ground state and 2p state. Okay, so before I do that, let me, yeah. So this is a hydrogen problems. Okay, hydrogen atom problems. That means um, ideally you will have energy of a hydrogen atom. Uh, if you remember in the in hydrogen spectrum, maybe I can write it on the sides, something like En is equal to minus of mz square e to the power 4 divided by a n square h square f n square, right? This is which we solve in the week 2. Okay, how do we get the energy of a hydrogen atom? And quantum mechanically it is given differently. Okay, I mean, how do we solve the problems? So this is what we use from Bohr's theory. So if you remember also last class we talked about hydrogen atom, but that is also without perturbation. Okay, and maybe before solving, let me just give you again terms or formula which is required. Okay, so in a hydrogen atom, what happens? Potential V of R is given to be minus of E square by R. This is the potential. Now the solution in a spherical polar coordinates, we talk about that psi of NLM r theta phi. It will be given by the radial part, which is a function of r, and the angular part, which is a function of theta and phi, right? Or the spherical harmonics, which is a function of theta and phi. Now r of NL is given to be minus 2 divided by n a naught. A naught is the Bohr's radius, okay? 3 by 2 and n minus of L minus of 1 factorial divided by 2n and n plus L factorial whole cube 2r divided by n a naught to the power of L e to the power minus of r divided by n a naught L 2L plus 1 n plus L 2r divided by n a naught. Okay, this is a very long-term equations. Okay, it's very long. Most of the time is given to you. Okay, most of the time is given to you, or I don't think so. It's necessary to memorize these terms. Okay, but you can but if you get to know few terms of the ground state excited state will be very helpful in solving the numerical problems. Okay, have an idea of how they are related to. So this is the radial part. Okay, I'm talking only the radial part. So the radial part R10, that means what is the case? R10 means your n is equal to 1, your L equal to 0. Okay, R10, that means n is your this n and L are the principal quantum numbers, right? N is n, L, m, and so on. So R10 will be equal to 2 a naught to the power 3 divided by 2 e to the power minus of r divided by a naught. Okay, how do I get this? I substitute by putting n is equal to 1, n is equal to 0, and also few properties of your term L here. Okay, and yeah, so here also here all of these equations here are available in that textbook. Okay, all of the derivations are available in textbook, and how do we get R10 also is available there. Okay, I'll just giving you a few terms which is required for this problems, and then R20, which is a function of r, is 1 by 2a naught cubed 1 minus of r by 2a naught e to the power minus of r by 2a naught. Okay, this is R20. Then R21, that means n is equal to 2, L is equal to 1. Right? They are different states, which is given by the root over by 6a naught cubed r divided by 2a naught e to the power minus of r by 2a naught. Okay, so this we will be using in the problems. Okay, in that numerical problems. Now, if you want to understand more about this, let me write n, L, orbital, m value, degeneracy value, and En. Okay, so when n is equal to 1, L equal to 0, this is given with R10, right? Orbital means s orbital, m equal to 0, degeneracy is 1, and energy is equal to minus of e squared over by 2n. Okay, that is first one. When n is equal to 2, there are two possibilities. Either L is equal to 0 or L is equal to 1. There are two things, correct? So here orbital, this will be s orbital and this will be p orbital. So L equal to 1 considered to p orbitals. M will be equal to what? Here m will be equal to 0. But here since L is equal to 1, so m is equal to from minus L to plus 1. That is 1, 0, minus 1. So if you talk about how many degeneracy, 1, 2, 3, 4. There are 4 degenerate states. Okay, and the energy of this is E square divided by A naught. Similarly, when n is equal to 3, L will be equal to 1. Sorry, L will be equal to 0, 1, 2. And this is s orbital. L is equal to s orbital. For L is equal to 1 is a p orbital, and L is equal to 2 is a d orbital. So m will be equal to what? 0. And p here, m will be 0, 1, 0, minus 1. And here will be, since L is equal to 2, m will be 2, 1, 0, minus 1, minus 2. And degeneracy will be 9, because 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 possible states, and the energy is minus of E square divided by 18A0. Okay, so that is how, if somebody talks about the s orbitals, that means you can understand, okay, L is equal to 0, n is equal to 1. Okay, in that sense. Okay. Now, that is the radial part, and similarly the spherical polar harmonics, spherical harmonics, okay, that is y Lm, which is a function of theta and phi, right? Again, I have given you the formula last class. So y, I'll just write here, y of 0, 0, which is of theta and phi, is 1 by root over of 2 pi. Y of 1, 0 of theta and phi is root over of 3 divided by 4 pi cos theta, and y 1 plus minus 1 theta and phi is equal to minus plus 3 by 8 pi e to the power plus minus of I phi sine theta. Okay, so this is also, what does it mean? Y 0, 0 means L is equal to 0, M equal to 0. Okay, why I wrote this important is because you will need to solve this particular the problems. Okay, so now, yeah, so let's go back to the problems which is given to you. Okay, the problems. So it says that consider a hydrogen atom which is subjected to a small perturbation. H prime is equal to lambda r square. This is the perturbation given to you, and use the first order correction to calculate the energy of the ground state and the 2p state. Okay, so automatically now you can have in your mind when somebody talks about the ground state, this is the most likely it's a ground state. This is what the most likely. This is the ground state energy. Why? Is because n equal to 1 and the energy is also n is equal to 1 and L is equal to 0. This is the ground state energy. Okay. So for your ground state, what does it mean? It means it is a state 1s. That means n equal to 1 and L equal to 0. Okay, so n equal to 1, L equal to 0 is the ground state. Now, or we can also m equal to 0. Okay, so psi of n L m now will be equal to r. N and L will be equal to 1, 0. L and M will be 0, 0. Okay, so now you know R10 is given to you here. R10 is given to you, and Y00 is also given to you. So you can easily substitute here, which is equal to 2A0 to the power minus 3 by 2 e to the power minus of r divided by A0. This is from the R term, R10. Y00 will be 1 by root over of 4 pi. So you will be getting 1 by root over of pi A0 q e to the power minus of r by A0. Okay, so now you know the wave function. So what is the energy correction? We have already written the formula. Energy correction En1 will be equal to what? Your ground state energy. That is 1, 0, H prime 1, 0. Or we have already written as En1 is simply psi H prime of psi. That means we just have to solve the perturbation potential, okay, which is H prime. Now, see, this is already given to you, or I can rather say if you convert this one into integration, we'll get something like psi 100. And anyway, this is the ground state energy, right? And your perturbation is given to be lambda r square, correct? And finally, you also have psi 100. But since this is a three-dimensional problem, so you have to add dv, not dr or dx. So not dx, dy, dz. You have to add dv. Not simply one dimension. If it is a one dimension, right, you write dx, or if it's a two dimension, you have dx, dy. But since in this case we are talking about a three-dimensional problems, hydrogen atom, you have to add dv. Okay. Now, this is simply like a much more simplest problem now, because you already know psi 100. This is equal to psi 100. You already have a psi 100, and you can just solve this numerical integration. So what happens to psi 100? You can just add integration of 0 to infinity of your r part, 0 to pi of your theta part, and phi part 0 to 2 pi. Why I'm saying this one? Because psi of 100 will be equal to 1 divided by pi a naught cubed, right? E to the power minus of r divided by a naught whole square. Why I'm saying? Because I have to put psi 110 and psi 100, and also lambda r square will be there. Okay, and other than this, this dv is given to be r square sine theta dr d theta d phi. If you expand the dv term, you will get r square sine theta dr d theta d phi in terms of spherical polar coordinates. Now you can take lambda outside because it is a constant term, and pi a naught cube also is a constant term, and there's a square term. You get pi simply pi a naught cube. Okay, then you get 0 to infinity, and there is an r square term, there is an r square term, and this is the r. So you get r to the power 4, r square into r square, and there is a e to the power minus of r by a naught term. So you can get e to the power minus of 2r divided by a naught, right? Because it's a square term. Now into dr, the same thing, 0 to pi, and for the theta term you have sine theta and d theta, sine theta d theta. And what about for the phi part? 0 to 2 pi, right? And you have only simply d phi. So if you substitute these problems, I mean if you substitute all this sine theta, d theta, you will get something like this will be equal to 4 lambda divided by a naught cube. That means you just solve this integration of sine theta using a different integrals, and this term here I can give you using the specific integration, or the standard integration, not specific integration, standard integration, 0 to infinity x to the power n e to the power minus of ax dx is equal to n factorial divided by a to the power of n plus 1. Okay, you can use directly this one. So now a means, in this case, a is equal to minus of 2 divided by a naught. Okay, sorry, plus 2 by a naught. Okay, so what happens is that you will get n factorial. So n factorial is 4 factorial in our case, and 2 by a naught to the power of n plus 1. So n plus 1, n is already 4, so you get 5. Okay? So this will be equal to 3 lambda a naught square. So this is the first order correction term to the ground state energy. Okay, so other than the ground state energy, which you already know of a hydrogen atom, you have to also add this term En1. The first order correction, which is equal to 3 lambda a naught square, if you subject a hydrogen atom to a perturbation of given by lambda r square. Okay, so that is one part. Now the second part is you have to solve the same thing for your 2p state. Right? This is for the ground state, which is equal to 1s state. Now it's also given to your problem to solve for the 2p state. So what is 2p here? 2p means n is equal to 2, l equal to 1, m should be equal to 1, 0 and minus 1. Right? Now again you have to do the same thing. You have to first find the r, the radial part, r, and l, we get r21. So r21 is given here, right? R21 I have given it to you. Yeah, r21 is this term, so which will be equal to 1 divided by root over of 24 a naught cubed r divided by a naught e to the power minus of r over 2 of a naught. Okay, it's very helpful if you can relate the ground state energy of R00, R21, R11 and so on. It will be very helpful while solving the numerical the problems. Okay. Now, so again, you can write again the y theta part and so on, but y theta part will be again 1, 0, minus 1 because you will need y of ln. So what we will do in this case is that e to p of the first state is equal to psi of nlm. Okay, the same thing, lambda r square psi of nlm.
Okay, this is your first order correction term as we have already written the formula before. Now, what happens is that if you look, notice carefully again, you can take the constant term outside, okay, and you will have only the radial part, theta part, and phi part. So you get 0 to r, 0 to 2 pi, sorry, 0 to pi for the theta part, 0 to pi, and for the phi, 0 to 2 pi. Okay, so r and l, right, and y l m, and what you will get? You get r square here, correct, and again r and l, r and l, y l m, and again r square sine theta dr d theta and d phi, right? This again is the same thing. You just instead of putting psi, you can just put radial part into the harmonic, spherical harmonics, and this one also, and you put the perturbation part as well. Now, what we can do is that you can separate the radial part and the theta part and phi part. So you can write r 0 to infinity. Sorry, this is 0 to infinity, and we get r and l whole square, and this is r square, this is r square, so we get r to the power 4 dr, and again 0 to pi, 0 to 2 pi, because this term consists only the theta and the phi part. You can simply write ylm, right, because this is consists only the theta and the phi part square. This is sine theta d theta and d phi. So this term usually tends to 1, okay, goes to 1, so you don't need to even solve that this integration. That means you require only lambda 0 to infinity, r of this will be equal to 1 by r and l, right? R and l means r to 1 in this case, right? You substitute it and square it, you will get 1 by 24 a naught cube r square divided by a naught square e to the power minus of r divided by a naught into r to the power 4 dr. And take outside the constant term, we get lambda divided by 24 a naught 5 integration from 0 to infinity r to the power 6 e to the power minus of r divided by a naught dr. Again, here also you use the same integration. Again, you encounter the same problems, which is integration from 0 to infinity of x to the power n e to the power minus of ax dx, which is equal to n factorial divided by a to the power of n plus 1. But a here is simply 1 by a naught, right? Because it is this term here 1 by a naught. So a here is simply 1 by a naught. So you will get lambda by 24 a naught 5 into a naught to the power 7 into 720. You will get 30 lambda a naught square. Okay, so in these problems, what do they mean is that suppose you have a hydrogen atom, and solving a hydrogen atom is easy. Okay, you can easily get the energy, which you can we already got in the first few classes also. But now when we introduce a perturbation other than the original energy, that means you have to also add the first order correction term. Okay, there is also second order correction term and so on. But according to the problems, you have to solve the first order corrections for the ground state as well as the excited as well as the first excited state. First excited state means we are talking about the 2p state. That means n is equal to 2, L is equal to 1. In the ground state, we are talking about n is equal to 1 and L equal to 0. So if you are talking about the ground state, you can refer from this whatever I have given it to you, this table. So when n is equal to 1, L is equal to 2, this is the ground state. First excited we get n is equal to 2 and L is equal to 1. Right? This one. So this is the first excited state. N is equal to 2, L is equal to 1, this one, and so on. Okay? So so that means if there is a perturbation potential, you have to solve the energy correction term. So the next problem is also very much similar to this, again to the same problems. Okay, same questions, similar problems, or similar approach, I would rather say similar approach. The question is about harmonic oscillator. So I think this is your question number 2, right? Question number 2 of your assignments. Okay, this is related to your harmonic oscillator. Harmonic oscillator. Again, let me just revise back whatever we have done. So if you have V of x is equal to a potential of half of m omega square x square. Okay, a harmonic oscillator has of this much has a potential of this form. I will tell you. Have a potential of this form, and the energy of this case will be simply n plus half h cross omega, where n equal to 0, 1, 2, and so on. Okay. Where 0 is the ground state, first is the excited for n is equal to 1 is the first excited state, n is equal to 2 is the second excited state, and so on. Now we are talking. Let's say we are talking about the 3-dimension. In 3-dimension, the potential will be a potential of x, y, and z, which is equal to half of m omega x square plus of half m omega y square plus half of m omega square z square. Suppose if the potential is in the 3-dimension, so what is the energy? The energy will be En of nx of ny of nz will be equal to what? First it will be n plus half h cross omega x, okay, plus it's the same thing, but it will be at x term, y term, and z term. N plus half h cross omega y plus n plus half h cross omega z. Okay, just like we have one dimension E is equal to n plus half h cross omega, here also we have 3 terms which is corresponding to x term, y term, and z term. Okay. Now there is another term. Called isotropic. What does it mean by isotropic? Isotropic means in this case your omega x is equal to omega y equal to omega z. That means they have the same frequency. That means in such cases you can write the energy En, which is equal to nx, ny, nz, to be simply, so this you can write simply omega, this you can write simply omega, this you can write simply omega, correct? Then you can just take common h cross omega and add all the term, right? Because this should be nx, this should be nx, this should be ny, and this should be nz. Okay, so you can take common h cross omega and add all the term. You will get nx plus ny plus nz, and half here will be plus 3 by 2 and h cross omega. Okay, so this I think you remember. I have just just revised whatever we have done previously, that if you have a potential of half of m omega square x square, you will have the energy given by a quantized energy term n plus half h plus omega, and for a 3-dimension you can just again add x term, y term, and z term. Okay, so so again you have the energy term. Now you also have the wave function, right? The wave function psi of n of x is equal to 1 divided by the power of pi 2 to the power n factorial x0 e to the power minus of x square by 2 x0 square hn of x by x0. Okay, so this is the wave function of your 1-dimension harmonic oscillator, and we're given by this term is actually, you can it's called as a Hermite polynomial, is given by h1y equal to minus of 1 to the power n e to the power of y square dn divided by dy to the power n e to the power minus of y square. And this thing is given by h0 of y equal to 1, h1 of y equal to 2y, and h2 of y equal to 4y square minus. Okay, so this is just a revision for you all, such that you can you can go back and have a look at it. Okay, so when you solve the harmonic oscillator, you will get this wave function psi of n, which is given in terms of n term, and you also have the energy E of n. And h0 of y means h when n equal to 0, h1 of y means when n equal to 1. So you will have again the ground state, the first excited state, and third excited state, and so on. Okay, that means the higher energy state. Now, if you look at your question number 2 from your problems, what does it say? It says that consider an isotropic harmonic oscillator, okay, in two dimension. Here is given in two dimension. Okay, given by h naught. This is your original Hamiltonian, which is equal to px square by 2m plus py square by 2m plus m omega square divided by, sorry, uh, okay, I think there is some my network issue is there. I think now it's going well. Okay, so yeah, so this is the m omega square x square plus y square. So this is the same thing, right? This is the same thing, like whatever I have just shown just now. This is px square, this is your kinetic energy, and this half of m omega square x square, this is your potential energy, and this problem is given in two dimensions. So now the question is, okay, what are the energies of the three lowest lying states? Okay, the question is what are the three lowest lying states? Okay, and corresponding degeneracy. Okay, degeneracy means how many number of states having the same energy. So we will look into it. Okay, solution. So first of all, we have to find out what are the three lowest lying states and what are the corresponding degeneracy. So for 1D harmonic oscillator, OSCI and W. For 1D harmonic oscillator, you know the energy is equal to n plus half h cross omega. But since in this case it is a 2D, for 2D, right, you get E n x comma of ny equal to nx plus half h cross omega x plus ny plus half h cross omega y. But again, since it's a harmonic, since it's an isotropic, omega x is equal to omega y, just what we have said, omega x is equal to omega y, then you can add both them together, nx plus ny plus 1 h cross omega, where nx comma ny can go from 0, 1, 2 and so on. Okay, so let nx equal plus ny be simply n, so that you can write that simply energy is equal to n plus 1 h cross omega. Okay, so this is just the formula of the energy. Okay, now for the ground state, the first one is your ground state, correct? The first state is your ground state. That is the lowest energy state. You have what? N is equal to 0. Right, n is equal to 0 is the lowest energy state. That means what happens? Nx should be equal to 0, and y is also equal to 0. This is your lowest energy state. Then what happens? En is given to be n plus 1 h cross omega is simply h cross omega, because n equal to 0. And what is the degeneracy? Because there is only one energy term possible here, so degeneracy equal to 1 for the state nx equal to 0, and y is also equal to 0. Okay, so that is the first lowest state. Now comes the n equal to 1. That is the next higher energy state. Okay, what is nx is equal to, n is equal to 1. So for n equal to 1, you will have nx equal to 0, possible ny equal to 1, or you also have nx equal to 1 and ny equal to 0. These are the two possible states. Okay, then what happens? We get energy will be 1 plus 1 h cross omega will be 2 h cross omega. And what is the degeneracy? Degeneracy, there are two terms here, right? So degeneracy will be equal to 2. For what? For the state what? Nx equal to 0, comma 1. That is a one state, comma, and the other state is 1, comma 0. So there are two states with 1, 0, 1 and 1, 0, which has the same net energy. Okay, So this is one thing. Uh, this is the three. I would rather say this is the three lowest lying states. Okay, three lowest lying states. There are three states, and all of them have different energies. So the first one has energies h cross omega, and the second term, when n is equal to 1, you will have two possible states with energy 2h cross omega. That means these two states nx is equal to 0, ny equal to 1, or nx is equal to 1, ny equal to 0. They are both having the same energy states. That is what they are called as the degenerate states with degeneracy g is equal to 2. Okay, just a second, please. Sorry. Yeah, so that is your first that is your first questions. Okay, that means you calculate what is the energy state, and also you calculate what are the possible degeneracy. And if you want to calculate the next high energy state, that means what? N equal to 2. If you want to calculate the next high energy state, n is equal to 2, that means what happens? The possibility is that nx equal to 0, ny equal to 2. That is the first thing. Second thing is nx equal to 1, and y is also equal to 1. There is also possibility because your n, which is equal to nx plus of ny equal to n, correct? And this last is nx equal to 2, ny equal to 0. That means ideally you will have what? Degeneracy equal to 3. And what is the energy? Energy is equal to nx plus ny is equal to 2 plus 1 h cross omega, which is equal to 3 h cross omega. Okay, so in this case you have degeneracy equal to 3 with the energy for the states 0, 2, 1, 1, 1, and 2, 0. Okay, these three states are also what? Are also of the same energy. That is why they are called degenerate states with degeneracy g is equal to 3. This is next higher possible states. Okay, so that is the first question. The first question is to list out what is the energy and what is the degeneracy. Now, the next question, which is also important in the same problem, question number 2. I think this is section B. The B is when you apply a perturbation. Again, come to the perturbation. When you apply a perturbation, what will happen to the energy terms? Okay, that is the question. Whether it will you have to add or you have to subtract. Okay, that is what the question is. So the question is that if we apply a perturbation V is equal to delta m omega square x y. This is given to you. A perturbation is given to you, and the question is find energy eigenstate. Okay, find the energy eigenstate and corresponding first order correction to all the three lowest line states which we have just calculated. So the idea is that first we have to find the energy eigenstate, and the second is that we have to introduce the energy correction, first order correction, which is equal to En1. We have to find this term again. Now, solution. What is the first state that we have just talked about? The first state is nx equal to 0, ny equal to 0. So that means we are talking about the wave function psi nx ny, which is equal to psi 0, 0. Right, so that means you have to multiply psi x into psi y with nx equal to and ny is also equal. That means what you need to do is that you just need to multiply these two equations. This one, you just to put n equal to 0 for one time for x and one time for y. What you will get? You will get this. You will get this equation, 1 by root over of pi alpha. Okay, alpha is the same. Alpha square is equal to m omega by h cross. Okay, or I think in the previous case I have written this one as x naught. It's also the same. X naught square is equal to m omega by h cross. Okay, either way, it's just a representation. And exponential of minus of x square by 2 alpha square. Okay, that is for nx equal to 0, multiply 1 divided by root over of pi alpha exponential of minus of y square by 2 alpha square. Okay. So this is the energy state. I mean, it's easy to find the energy state. You just need to know what is the ground state. Psi nx equals 0, psi inverse 0. Then you just need to substitute what is the wave function. Then you can just multiply this term and this term. You will get 1 divided by root over of pi alpha, right? And again you can x square and y square can be added up together, minus x square plus y square by 2 alpha square. Simple as this. Okay, this is for the state 0, 0. Okay, so that means your ground state energy, I mean the first question, which is find the energy eigenstate, is done. Okay, for the first term. Now again you have to find the first order energy correction for this particular state. So E1, 0, 0, right? That is the energy one. Again you are talking dx dy, because it is a two-dimension dx dy. You get minus infinity to plus infinity of x, minus infinity to plus infinity of dy will be something like psi 1 1, psi 1, so sorry, psi 0 0 star, and the potential perturbation potential psi 0 0 dx dy. This is the formula which you have, if you remember it, this is the perturbation formula of energy correction. We get even something like psi n h prime of psi n, something like this, right? And here the perturbation is already given for you to be, I just have represented to, instead of phi prime, I just represented it p prime. Okay, that means it's the same thing. What you have to do is that integration from minus infinity to plus infinity, you substitute psi 0 0, and psi 0 v prime here is given what? V prime is delta m omega x square. So that means this is delta m omega square xy. Okay, so what you need to do is that since this is delta m omega x square, you can just take it out aside because they are all constant, m omega square divided by, here also you will have, if you multiply here, you will get something like pi alpha square minus infinity minus of infinity x, because x comes from here, e to the power minus of x square by alpha square dx, and similarly minus of infinity to plus of infinity y, e to the power minus of y square by alpha square dy. This is, we just substitute what is the wave function that we have already obtained from here. This is psi 0 0. Okay, we just substitute it here, and now this term and this term goes to 0. So that means there is no, for your ground state energy, there is no correction. That means it is the same thing as your original state. Okay, that means the energy is the same, because E1 0 0 is equal to 0. That is the first order correction is equal to 0. That means you don't have the need to do any correction. Now we will move to the next state. This is the ground state which I have just talked to you, right? N equal to 0. See, for the n equal to 0, what you have done is that you know the energy which is equal to h cross omega, and you also know what is your wave function psi 0 0, and the energy correction also to be equal to E0 0, which is equal to 0. Now we are talking about the next state, which is equal to n equal to 1. And n is equal to 1, how many? You have 0 1 and 1 0. So then what happens? You have to write the wave function for 0 1, right? 0 1, which is equal to psi of 0 1 x1. That means psi n x, which is psi of n x y, which is given to you. You substitute n equal to 0 for x, and you substitute n is equal to 1 for y. So what you will have, you will get something like this. Pi alpha, this is, you already know this is for n equal to 0, x square by 2 alpha square. But for n equal to 1, you will have root over of 2 root over of pi alpha cube y exponential of minus of y square by 2 alpha square. It's the same thing. You just need to substitute the wave function for x equal to 0 and ny equal to 1. Similarly, for 1 equal to 0, that means psi 1 0 x comma y, you will have something like 2 divided by root over of pi alpha cubed. Here instead of y, you will have x e to the power exponential of minus of x square by 2 alpha square, and then this term here will be coming 1 divided by root over of pi. Sorry, here is another term here, and then alpha e to the power minus of y square by 2 alpha square. Both this equation are the same, right? Both equations are the same, except that in the first thing you put nx equal to 0 and y equal to 1. In the second case, you get nx equal to 1 and ny equal to 1. And how do you get this equation? You get the equation by going back to the main equation, which is given by you by this one. So you need only the general equation of a harmonic oscillator, and you put n equal to 0, n equal to 1, and so on. Okay, depending on the situation, you put n equal to 1, n equal to 0, and so on. And if it's a two-dimensional problem, you just multiply nx into ny. That means the wave function also will be multiplied. Okay, that is what I'm doing here. So this is for the second case. Now your energy state is done. So the next question is to find out the first order correction term of these two states. Okay, that means sorry. Yeah. Why I'm not able to. Okay, so let me. Okay. Sorry, let me just restart the sharing. Yeah. Okay. So we just need again to find out the energy correction term, something like E and 1, right? But here you will get something like 0, 1 term, and also E of 1, 0, something like this, right? That means you have to find you have to solve the first order correction for both the state 0, 1 and 1, 0. Now to do that, again we will use your secular equation. You have to use your secular equation. And the secular equation, if you remember, you will have something like let's say if this is your 0, 1, you will get something like 0, 1 state, and this is, let's say, your sorry, it should not be like this. It should be something like your W11, W12, W21, and W22. Okay, so we will solve, and then we will use this equation. Okay, so the first thing we will talk about 0, 1 state. Okay, how is the first energy correction for this one state? If you remember, we will use again this equation which is given to you, psi n h prime psi n. So that means ideally you will have to solve this equation 0, 1 v prime 0, 1, right? So this will be your first correction term, which is equal to 1. 0, 1, you know the wave function, this is given to you 0, 1. So again v prime is also given you delta m omega square xy. So you can get something like delta m omega square divided by root over of pi alpha 2 divided by root over of pi alpha cubed. Okay, and then you do the integration for the x and y. So minus of x to minus of infinity to get x exponential term minus of x square by alpha square dx, and similarly for your dy, you get minus infinity to plus infinity y square e to the power minus of y square by alpha square and dy. Since this is an odd term, so it will be goes to 0. So the whole term is equal to 0. This term. So the first term is anyway the first order correction term, that for your 0 state, that is equal to 0. I mean for your 0, 1 state is equal to 0. Similarly for your 1, 0 state, v prime 1, 0, this also if you solve you will get 0. Okay, now there is another term. What is that term? 0, 1 state from here, v prime, and 1, 0 state from here, right? So that in this case what you will get is that I'll just write it out, 2 delta m omega square by root over of pi alpha cube 1 by the root over of pi alpha. Okay, integration from minus infinity to plus infinity. Again, it's the same thing. You just need to substitute again 0, 1 and 1, 0 here. So get x square exponential of minus of x square by alpha square dx. This is your dx term, and your dy will be equal to minus infinity to plus infinity of y square exponential of minus of y square by alpha square dy. And this term, if you solve, again, if you solve this equation, you will get something like half delta m omega square h cross 1 by m omega. Okay, that means you use this formula x square e to the power of a of x square. Again, you can use the same formula which is there, integration from 0 to infinity of x and e to the power of a of x d of x. Okay, this is a standard integration which is available. Okay, and since you get this one, similarly your another state which is 1 0 v prime 0 1, this is also to be half yeah, so this will be equal to simply half h cross delta omega. This is also half h cross delta omega. Now you get all the terms in a matrix. That means v prime, you get one. The first one is 0, that means 0 1 0 1, that is 0, and the second term will be 0 1 1 0, that is will be something like half h cross delta omega. The third term also half h cross delta omega, and the fourth term will be equal to 0. Right, now you use your v prime minus of lambda, or you can write e and 1 also, I will be equal to 0. That means 0 lambda minus of 0, so you can write something like lambda and half h cross delta omega, and here we get half h cross delta omega, and then this is 0. Oh, sorry, this is lambda, not lambda. It's confusing lambda. You can write e and 1, something like this, and here also e and 1. So here this is equal to 0, which implies that what will happen? You can get something e and 1 is equal to, this is just a determinant of the matrix, which is equal to plus minus half h cross delta omega. So now your energy term will be added by and subtracted by this term. So one energy one energy term will be added by half h cross delta omega, and the other energy term will be minus of half h cross delta omega. So your energy now, the original energy will be simply, instead of, if you go back, what is the original energy? Your original energy is this term, is this one, twice of h cross omega. Right, so twice of h cross omega, what will happen? You will get twice of h cross omega, and then plus this term, plus of e and 1. Right? Your e and 1 is equal to plus minus of half of h cross delta omega. So you will see that other than the original energy term, you also have to add one more correction which comes from your correction term. Okay, so we are almost finished the perturbation part. So in the perturbation part, what you need to do mostly is to question usually asks how to solve the first order energy correction. Okay, first order correction, that means you just solve the equation which is already there, which is given by psi perturbation psi. Okay, you can just solve, or I can in this equation, right, psi, sorry, suppose you just need to solve your e n 1 to be equal to psi of n, h prime which is due to your perturbation, and psi of n. Okay, so you just need to solve the equation and then add in your original energy equation. So whether it is a harmonic oscillator or whether it is a hydrogen atom, is the same thing. Okay, you just need to solve this equation and then add it up to your original energy term. Okay, now we will move to a little different concept called Zeeman effect. Okay, so we will move to a slightly different problems now called Zeeman effect, and this is your question number 3 in your assignment. Okay, so maybe let me just okay, this is much more simpler. Okay, this is much more simpler. I think whatever you have done. So what is the Zeeman effect? Maybe I can just write here what is the Zeeman effect. So splitting of spectral lines. Okay, splitting of spectral lines in a magnetic field. Okay, so if there is a splitting of the spectral lines mean the transition from one state to the other state in the presence of the magnetic field, that is because due to the interactions with the magnet and the field. Okay, so that is your Zeeman effect. So there are two things is that normal Zeeman effect. Normal Zeeman effect, what happens is that if there is no Zeeman effect, you will have something like frequency of transition from one state to another state, you will have mu is equal to mu naught, simply mu naught. But if there is a Zeeman effect or the interactions with the magnetic field, you will have mu is equal to mu naught plus EB by 4 pi m del of ml. Okay, and this the selection rules for del of ml will be equal to 0 plus minus 1. So that is why if you look at it, you will get, therefore mu, you will get mu naught. Mu is equal to mu naught plus of EB by 4 pi m, right? And also mu is equal to mu naught minus of EB by 4 pi m. So each line now it will be split. It will be split into 3 lines with mu is equal to mu 0, mu is equal to mu 0 plus of EB by 4 pi m, and mu is equal to mu naught minus of EB by 4 pi m. Okay, this is the normal Zeeman effect. There is another one called anomalous Zeeman effect. So in the case of an anomalous Zeeman effect, what happens is that it's the same logic, is that mu is equal to mu naught plus GMJ EB by 4 pi m. The only difference is that in your first case, your spin is not contributing, S is equal to 0, but here your S is not equal to 0, your spin is not equal to 0. That is why you have this G term, which is related to your 1 plus of J plus 1 plus of S plus 1 minus of L plus 1 by 2J plus 1. So what is J? J is the sum of your orbital angular momentum and the spin angular momentum. Okay, quantum numbers. Okay, that is why you have this G term here, because here S is not equal to 0. You also have the magnetic quantum number mg. But here what happens is that since S equal to 0, so you have only J is simply equal to L. Okay. Now, so the first questions from your problems, let me just have a look at the problems. Okay, so I'll not write the problems, is available with you. So what is the problem? The problem is you have to consider a transition from L equal to 2 to L equal to 1, right? So then ideally without the, let's say without the interaction with the magnetic field, will have only one transition, ideally, right? But since the question is that consider a normal Zeeman effect, right? So this one will be completely wrong, because this is a transition without the magnetic field. But when there is a magnetic field, what happens is that L equal to 2, that means these, let me redraw it. This is L equal to 1, this is L equal to 2, and this is L equal to 1 is given in your problem. Now it will be coming what? L equal to 2. So L equal to 2 means ML will come to be 2, 1, 0, minus 1, minus 2. And when L equal to 1, ML will be equal to 1, 0, minus 1. So instead of one line, now it will split into 5 lines. This, and this is 2, 1, 0, minus 1, minus 2, and this again, this will goes to, this is 1, this is 0, and this is minus 1. Why? Is because there is also a quantum number ml. Okay, that is why a single line now split into 1, 2, 3, 4, 5 for L equal to 2. For L equal to 1 is split into 3 lines. Now what is the selection rule? The selection rule is delta ml equal to plus minus 1. Okay, and 0 plus minus 1. So now you have to find out all the possible combination in which delta L equal to 0 plus minus 1. So the first thing is that -2 to -1. That is one transition line which you can go, right? Because -2 plus minus of 1, you will get minus of 1. So delta ml is equal to -1. Second is that this transition from -1 to 0, and the transition is 0 to -1. So this transition is delta ml equal to -1. Now the second is from 0, from 0 to from delta ml from minus of 1. So minus of 1 to minus of 1, 0 to 0, and 1 to 1. This is delta ml equal to 0. Okay, and finally what happens is that from 1 to 0, that means let's say from 0 to -1, 1 to 0, and 2 to 1. This is again another transition with delta ml equal to +1. So you see that there are mainly 3 lines, okay, 3 transitions. There are 3 transitions. There are 3 transitions with what? With delta ml equal to -1 and 0 and +1. Okay, so now if you want to write out the frequency, that means there are 3 transitions, 3 main transitions. Okay, and mu will be equal to mu0. Again, we get mu is equal to mu0 because delta ml here is equal to 0. So delta ml is equal to 0. That means your mu is equal to mu0. And if delta ml is equal to +1, we get mu naught is equal to EB by 4 pi m. And here is mu is equal to mu naught. If delta ml is equal to negative, we get EB divided by 4 pi. Okay, how do I get this? I just use the general formula here. So delta ml is equal to 0, delta ml is equal to 1, and delta ml is equal to -1. Okay, so this is one problems in which you can find out how many number of transitions are there. Okay, now the second part of the problems is consider a sodium. Consider the anomalous Zeeman effect for sodium D1 and D2 lines. So D1 corresponds to what? Transition from 2p half to 2s half, and D2 lines correspond the transition from 2p 3 by 2 to 2s half. Okay, so we'll solve one by one. Okay, we'll first solve the D1 lines. D1 lines is 2p half to 2s half, right? So that means 2p half, this is one transition. But here, remember, here is this anomalous Zeeman effect. That means you are talking about the J part also, the total angular momentum. So that means mj will be equal to, this is half minus of half. So this is J equal to half. Here you will have mj value. This is mj, which is equal to plus half and minus of half. So similarly, 2s half also will split into plus half mj value and minus of half mg value. Okay, and you also have to calculate the value of g, right? The value of g into mg, because it's also there in your formula. If you remember, the anomalous Zeeman effect, you have g into mg. You have g into mg value term. So what you need to do is that you can also calculate the value of g into mg, and g I have already given to you is equal to 1 plus jj plus 1. So here jj plus 1 is your j is equal to half, and remember for p l is equal to 1 and for s l equal to 0. Okay, so that is also there. That means this will be equal to what? The gmj, this will be equal to 1 by 3 minus 1 by 3 and 1 and minus of 1. Okay, so now what is the selection rule? Now it's very easy. Now what happens that you can transition from minus half to plus half. This is one transition, and there is another transition from here, because plus half, this is delta mj equal to 0, and another is minus half to minus half, and this one to this one. That's so easy. Okay, so your delta mu now will be equal to simply g mj eb by 4 pi f. So how many transition lines are there? 1, 2, 3, 4. 4 transition lines. Okay, so the transition line is like minus half to plus half, again half to half. This is again use the selection rule of delta mg. Selection rule delta mg. Okay, so ideally you will have seen only one spectral lines, right? But now there are 1, 2, 3, 4 spectral lines. Okay, now the D2 lines. D2 lines now is 2p 3 by 2 to 2s half. So how many transition lines are there? 2p 3 by 2. So you will have what? mj 3 by 2 half minus of half minus 3 by 2. These are the mj values, and j values here is equal to 3 by 2. And similarly 2s half, you will get something like half and minus of half. Okay, so again you can calculate again the value of g mj using the value of g, 1 plus jj plus 1 plus ss plus 1, that I have given you the formula here. Yeah, this is the value of g. So you know the value of j, you know the value of s is equal to half. If it is s equal to half, and l, you know whether it's a p state or the l state. If it is an s state, l is equal to, if it is a p state, l is equal to 1. So you can easily calculate it, the value of g, and you will get g of mj here will be something like 2, and this is 2 by 3, this is minus of 2 by 3, this is minus of 2, this is plus 1, this is minus 1. You just calculate the value of g of mj. So put the value of g and put the value of mj to be 3 by 2, you will get 2. Again, find the value of g and substitute mj equal to half, you will get 2 by 3. Now again, what we need to do, we can easily calculate it, minus half. The first transition is this transition, minus half to plus half, that is equal to minus 1, right? That is the selection rule for delta of mj. And then minus 3 by 2 to half, because again the selection rule will be minus 1, correct? Now that means how do you get the selection rule? This is minus of half, right? And this one is half, so minus of half, it will be equal to minus of 1. Similarly here, minus of 3 by 2, okay, and minus will become plus of half, will be equal to minus 2 by 2 equal to minus of 1. So this is the first transition. Okay, now similarly the other transitions are not allowed. So 3 by 2 to half, why? Is because your delta mj will be plus 2, are not allowed. Only delta mj equal to 0 plus minus 1 are allowed. Okay, so now what happens, you get half. Again, now the second part is will be half to half will be allowed, and minus half to minus half are also allowed. Now 3 by 2 to half are allowed, right? And half to minus half also are allowed. Okay, so use the selection in such a way that delta of mj equal to 0 plus minus 1. Then you will get what are the number of transition lines. So you get 1, 2, 3, 4, 5, 6 transition lines. Okay, so so ideally what happens is that now with the application of the magnetic field, you have different transitions possible. Instead of getting only one without the magnetic field, you get more than instead of getting only one transition, we get more possible, not the transition of the spectral, not the lines. Okay. So according to this questions, I think that is enough. And so the transition rules, remember the selection rules. The selection rules is delta L, let's say plus minus 1, delta ML will be equal to 0 plus minus of 1. Okay, so I think I will have one more question to solve from this week 4 assignment. Okay, and these problems, in this class, what we have seen is that we have solved mostly the perturbation problem. Okay, other than the ordinal state, other than the ordinal energy state that you have, you also introduce a perturbation, and when you introduce a perturbation, you have to solve the first order correction term or the second order correction term, depending on the problem. But mostly it's a first order correction term on the energy term. So you have to solve it and then add it up to your ordinal energy term. Okay. Other than that, I think there is not much. Okay. So all of these problems which I have which I have done is there in your assignment, and also most of this is also available in your ZLI textbook. Okay, Introduction to Quantum Mechanics, ZLI, and it's a very popular book, and details are also there. I can ZLI ZLI Introduction to Quantum Mechanics. I think. Okay, so any problems you can always look into it, because there are many solved examples there if you want to get to know more. And any question also you can always ask me, you can always mail me also, that is also fine. And in the next class what I will be taking is that I'll be finishing one more problems from this assignment, from the week 4 assignment, okay, which is still in the left, and also is the week 5 assignment I'll be taking. So I think today I will stop here, okay, and thank you for joining the classes. If you have any question, you can always ask, and maybe I'll see you around next week. Okay, thank you so much.